Assalamu alaikum wa rahmatullahi wa barakatuh. Welcome to another edition of this online class. Before we start, let me remind us. Please, let's copy our notes into our chemistry notes together with our assignments. And let me still remind us again, the response to our assignment is very low. Please, I will plead to us that we should do our assignments as at when due. Allah will assist us. Now let's go back to today's work, periodicity of elements, where we'll be looking at the periodic law, features of the periodic table, SPDF method of writing electronic configuration of elements, and then the last one, which is the quantum number. Now let's go to the periodic law. The periodic law was proposed by a scientist called Moseley, in which he arranged the elements in the periodic table according to their atomic number. The periodic law, it states that the property of elements are the periodic function of their atomic number. Now, these elements are in the periodic table. They are classified into group and period. We have 8 vertical columns called group, as from 0 to 7 or 1 to 8. We also have the 7 horizontal row called period. 7 horizontal row called period. Now, we also have the elements between group 2 and group 3, as you see in the periodic table, called the transition metals. And then we have at the bottom of the table here, we have the inner transition elements, or you call them the real earth element. That is the lanthanide series and the actinide series. Now, let us go to the group. The group 1 elements, they have 1 electron in their valence shell. Group 2 has 2 electrons in their valence shell, and it goes like that: group 3, group 4, and then group 8, which have a complete shell. The group 1 elements are known as the alkali metals. The group 2 elements, they are known as the alkaline earth metals. Group 3 elements, they are known as boron family, and it goes like that. The group 7 elements are known as the halogen. They are called the halogens, which is known as the salt formers. Then we have the group 8, which are called the noble gas, real gas. This is the group 8 here. The noble gas, real gas, or the inert gas, because they have a complete outermost shell. That is why they don't undergo reaction. They are inert. Now, let's still talk about this periodic table. The group 1 and 2 elements, we call them the S block elements. The reason being that they have partially filled s orbital. The p block elements, which are from group 3, 4, 5, 6 up to group 7, they are the p block elements. And because the valence the valence electron are in the p block, they have partially filled p orbital. Then we have the transition metals. These are the transition metals. The transition metal, they have partially filled d orbital, and that is why we call them the d block elements. We call them the d block elements. And down the group where we have the lanthanides and the actinide, we call them the F block elements. Group 1 and 2 are the S block elements. Group 3 to group 0 or group 8, we are called them the p block elements. I've told us the reason why they are called like that. Now let's go back to our table again. I've seen that table again. So this is our table. You can look at it very well, and then the explanation. Now the next thing is how to determine group and period. We have seen that the elements the periodic table is such a way that the elements are arranged in group and then period. Now let's see how we determine the group and period. If you remember in our KLM method of writing electronic configuration, that one only gave us the group. That one we can use that to determine only the group and the period of a particular element, where the group, the number of valence electron will give us the group, while the period, the number of shells will give us the period. Now this SPDF method of writing electronic configuration is more appropriate in the sense that it's going to give us not only information about the group and the period, it will also tell us whether that element belongs to the S, P, D or F orbital. So, and that is why it is better for us to use the SPDF method of writing electronic configuration. Now before I go further, the S orbital will carry a maximum of 2 electrons, P will carry a maximum of 6 electrons, D will carry a maximum of 10 electrons, and the F will carry a maximum of 14 electrons. Now let's look at the way these elements are filled in the energy levels. If you look at the arrow very well, you will see that we have 1s, 2s, 2p, 3s, 3p, 3d like that, and the arrow pointing downwards. This arrow is indicating the direction on how we are going to fill our orbital. First of all, we first fill the 1s, then you go to 2s, then you go to 2p, 3s, 3p, 4x like that. You see the way the arrow is moving? 3d, 4f, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p, and then 7n, and then it goes like that. It goes like that. So this method is in accordance with the Outbound Principle, which states that the lower energy level is first filled before we go to the higher energy level. That means 1s is lower than 2s, 2s is lower than 2p, and it goes like that. Now let's take an example. Write the electronic configuration of the following, where we have potassium 19, vanadium 23, copper 29, manganese 25. Now the solution. If you look at the solution very well, you will see the way we have arranged the orbitals according to their energy level. 1s is first filled before we go to 2s, 2p, 3s, and then it goes like that. Now this is the last orbital that is filled, which is the 4s, and it's giving us information that this particular potassium is in period 4, group 1, and then is a S block element. If you check the periodic table, you will see it very well. And then it goes for others like that. It goes for others like that. Now let's go back. Our quantum numbers now. According to Nebo, electron shell is assigned quantum number, and the quantum number, there are 4 in number. We have the principal quantum number, the subsidiary quantum number, which is also known as the azimuthal quantum number, the magnetic quantum number, and then the spin quantum number. Now let's take the first one, which is the principal quantum number. It gives us the value of n and indicates the position of the shell relative to the nucleus. That is how close a shell is to the nucleus. Now this n ranges from 1 to 2, 3, 4 like that. When n is equals to 1, that is the case shell, which is the K shell, which is the first shell. When n is equals to 2, we have the L shell. When n is equals to 3, we have the M shell. When n is equals to 4, we have the N shell. And these are the main shell. These are the main shell. Now let's go further. Now each of these shell has one or more subshells, and they are known as the SPDF subshell. The K shell, where n is equals to 1, has only one subshell, which is 1s. The L shell, which n is equals to 2, has 2 subshell, which is the 2s and 2p, and n, which is 3, has 3 subshell, which is 3s, 3p, and 3d. Then the n where n is equals to 4, that is the n shell, has a subshell of 4s, 4p, 4d, and then 4f, and it goes like that. Now this particular table gives us the summary of what we have been saying. If you look at this table very well, let me show you the table very well. If you look at this table very well, you see that the K shell, which is 1, has only one subshell, and the number of orbitals is determined by n square, where we have 1 square. The number of subshell is the number of electrons in the subshell is 2, and then it goes like that. For L, which is 2, we have 2s and 2p, and then n is equals to number of orbitals is 2, n square, which is 2 square, which is 4, and this is how we determine the 4. 1 plus 3 is 4. The next one is n, which has n value to be 3. Then n square, number of orbitals is determined by n square. 3 times 3 is 9, and this is how we get our 9. 3s has 1, 3p has 3, and then 3d has 5, so which is equals to 9. And then it's the same thing for the n, where the value of n is 4, like that. Now if you look at it, the maximum number of electron per shell is n square, 2n square. That is, if you calculate it, we have 2 here, 2 here, 18 here, 32. Now that is theoretically. That is theoretically. Practically, each of them, with apart from the K shell, which is the first shell, which carry a maximum of 2, any other shell will be carrying a maximum of 88 electrons. I just remind us, we know that before. Now let's move to our next quantum number, which is the subsidiary quantum number. The subsidiary quantum number, what that one is telling us is that what that one is describing is the position of an electron on the sub-energy level called orbital, and it is denoted by small l. Now the value of l depends on the value of n, which range from 0 to n minus 1. Now if n is equals to 1, which is the K-shell, 1 minus 1 is 0, and the orbital is s orbital. Now it goes like that. For n is equals to 2, we have seen that 2 minus 1 is 1, and that is p orbital. And then for this one, 2 is d orbital, and then 3, that is for the n shell, in which small n is equals to 4, is the f orbital. That is what this one, the subsidiary quantum number, is talking about. Now let's move on. Now each of these subshell has one or more atomic orbital. The question is, what is atomic orbital? Atomic orbital is a region around the nucleus in which electron is mostly likely to be found. Now this SPDF we have been talking about, is an initial used to describe a spectral line. That is S for sharp, P for principal, D for diffuse, and F for fundamental. Now the shape of this S and P orbital. The S orbital is spherical in shape and is symmetrical about the nucleus, while P orbital is a dumbbell shape. It looks like figure 8. It looks like figure 8. Now let's go back to the next one, which is the magnetic quantum number. This describes the splitting and the orientation of orbitals as a result of influence of magnetic field. The value of m depends on the value of l, which is the subsidiary quantum number. Now this m, what this one is telling us, that it is the value of l that will determine the value of m, and m ranges from -1 through to 0 to +1. Now look at the values. Where we have l to be 0, m will be 0, and that is s orbital. Where we have l to be 1, l will range from -1 through to 0 to +1. That means the P, which is the p orbital, which has 3 orbitals. Each of them is carrying a maximum of 2 electrons, and we have 3 there, which I have said before that the p orbital will take maximum of 6 electrons. Each of the orbital will be taking 2 electrons. Now where l is equals to 2, we have from -2 ranges from -2, -1 up to 0 +2, and where we have l to be 3, and then it goes like that. It goes like that. Now this table is just still telling us what we have been saying. S orbital has only 1 orbital, p subshell has 3, and then it goes like that. Now where we have the total number of orbitals in a particular subshell is n squared, as we have seen before. This one we have seen it before, where n is equals to 2, number of orbitals is n squared, that is 4. S and p are present there, and then it goes like that. Like I said before, an orbital will accommodate a maximum of 2 electrons. Now let's move to the next one. This table you have seen is giving us the summary. No, before that, the spin quantum number. Yes, that is the last one. The spin quantum number describes the spin of an electron on its own axis, and then the value is either plus, half, or minus 1, because it's either they spin clockwise or anti-clockwise. Now this table is showing us, it's giving us all the information about the 4 quantum numbers. If you look at it very well, is what we have been explaining previously. So let's move on. Now, principle we consider in describing electronic configuration of atom. One of the principles is the Pauline's exclusion principle. There are 3. We have the Pauline's exclusion principle, the Outbound principle, and then the Hund's rule of maximum multiplicity. Now let's look at the Pauline's exclusion principle, which says that no 2 electrons in the same atom can have the same value for all the quantum numbers. That is, if we have 2 electrons in the same atom, then if the value of n, you can see it very well now. If the value of n is 1, as we have seen before, l will be 0, m will be also 0, and then the spin, one will be spinning clockwise while the other one will be spinning anti-clockwise. That is what the Pauline's exclusion principle is talking about. Now let's move to the Hund's rule of maximum multiplicity, which says that electrons are distributed among orbitals of the same subshell singly before pairing up. That means in the same subshell where we have like this now. This one, we know we have 1 1 there. So let's look at this one. Where we have 3 electrons, you first place it singly first, then before we can pair it up. So, and that is why I said this, if you look at this example for nitrogen 7, which has 1s2, 2s2 and 2p3, the p will be divided among the 3 orbitals first singly, then before pairing up. Now let's look at another example. Number 2, that is example 2, oxygen 8. If you look at it, in the p orbital, the electrons are distributed 1 1, then the remaining one is placed in the first orbital to show that they are distributed singly before we pair them up. So let's move to the Outbound principle. We have stated the principle before. Energy of lower orbitals of lower energy is first filled before we fill the orbitals of higher energy. So that is that on that. Now let me, so that you see this question very well now. This example. Number 1, list the type of atomic orbital present in the atom of element represented by S8. If you look at the solution, first of all, before you can do this, you have to write the electronic configuration of that particular element. Now if you look at it very well, after filling it up, you see that the 2 atomic orbitals that are present there are S and P, and that is what they are asking us. List the type of atomic orbital present in that particular element. So that is that for that. Let's look at another question. Example 2. How many orbitals are occupied by electron in the atom of an element with atomic number 7. Then the second question says, how many unpaired electrons are in the atom? Solution. I told you the solution to that is that you first write the electronic configuration of that particular element using the SPDF method. If you look at it, we have 1s which has only one orbital, 2s which has only one orbital also, and 2p which has 3 orbitals. So the total number of orbitals there is 5. And then when you write the electronic configuration, you see that the 3 electrons in the p orbitals are what? They are unpaired. So that means we have 3 unpaired electrons there. So that is that for that question. Now let's look at another question. How many orbitals are in the third energy level and what are their composition? That is the question. The third energy level is what? N is equals to 3. And if n is equals to 3, the number of orbitals is calculated using the formula n square. So there we have 3 square, and 3 square is equal to 9. That means the number of orbitals there is 9. Now, they say what is the composition? The composition is that we have 1 3s because it's n is equals to 3. So we have 3s, we have 3 3p, and then we have 5 3d orbital. So 1 plus 3 plus 5 is equals to 9. So that is the composition of that is their composition. Now let's go to example 4. How many subshells are in the M shell? Then we should name them. M shell, you know M shell is the third energy level, so n is equals to 3. The number of subshells there is, we have 3s, 3p, and then 3d. That is the answer to that question. Now that is the end of our class. Our assignment is there on the board. Although that question 3 I have solved it, but you still solve that question 1 and then 2, and then you consult your textbook, solve many questions, as many as possible under this particular topic. Allah will assist all of us. Assalamu alaikum wa rahmatullahi wa barakatuh.